This is a number so captivating that it has persisted in our imaginations for more than 2,000 years. This number is so universal that it's found in the works of ancient Greek mathematicians, revolutionary scientists, renowned architects, and even in blockbuster novels and movies. It's so pervasive that it appears in the grandest architectural wonders of the ancient world, the masterpieces of the greatest Renaissance artists, and even in the atomic structure of recently discovered minerals. This number appeals to a wide audience, from designers, mathematicians, and mystics to doctors, biologists, and investors. It is found in the natural world, and is even inherently linked to our perceptions of facial attractiveness. Throughout history, it has been used to create beauty in many significant works of classic art and architecture, and it continues to create visual harmonies in modern graphic design, product design, photography and video composition, logos, user interfaces, and more. Some even believe it can be found in the proportions of the solar system, as well as in the price and timing movements of stock markets and foreign currency exchanges. It's like the hidden language of the universe. This is a video about the golden ratio, the divine beauty of mathematics. The term golden ratio wasn't actually used until the 19th century. It's believed that the first person to use the term golden was the German mathematician Martin Ohm. He used the term goldener Schnitt, which translates to golden section, in the second edition of his book Die reine Elementarmathematik, published in 1835. The term golden ratio made its first appearance in English in an 1875 Encyclopaedia Britannica article on aesthetics by James Sully. However, it wasn't until 1898 that the term was used in a mathematical context, in the book Introduction to Algebra by Scottish mathematician George Crystal. The golden ratio is an irrational number with an approximate value of 1.618. This number, represented by the Greek letter phi, extends infinitely without repeating. Similarly, pi is another irrational number, approximately equal to 3.14, which represents the ratio of a circle's circumference to its diameter. Throughout history, the golden ratio has been known by various names. Sometimes, it's denoted by the Greek letter tau in mathematical contexts. Today, it's most widely recognized as the golden ratio. However, it has also been called the golden number, golden proportion, golden mean, golden section, and golden cut. In ancient times, it was even referred to as divine. The ancient Greek mathematician Euclid first described it in Book 6 of his treatise Elements, stating, "A straight line is said to have been cut in extreme and mean ratio when, as the whole line is to the greater segment, so is the greater to the less." The magic and wonder of the golden ratio lie in its unique property. Let's consider a line that we can divide at any point. If the entire line length is 1, let's name it A, and we split it into 2 equal parts, we get 2 identical segments. We'll name the first segment B and the second segment C. Each of these segments is 1 by 2. In this scenario, the ratio of A to B is 2 to 1, and the ratio of B to C is 1 to 1. Now, let's divide that line again, but this time, imagine it as a chocolate bar that we're sharing. If I give you 2/3 of the chocolate, which we'll call B, and I keep the remaining 1/3, which we'll call C, the whole chocolate bar, which we'll call A, is still 1. In this scenario, the longer segment B is now 2 by 3, and the shorter segment C is now 1 by 3. The ratio of A to B is now 1 to 2 by 3, which is equivalent to 3 by 2. And the ratio of B to C is 2 by 3 to 1 by 3, which is equivalent to 2 by 1. No matter how you divide the line, the ratios of A to B and B to C are different, except for one special case. This special case fascinated the ancient Greek mathematician Euclid over 2,000 years ago. At this unique point, the ratio of A to B and the ratio of B to C are both equal to 1.618 to 1. This number is the golden ratio. This is one unique aspect of the golden ratio. The ratio of the whole segment A to the larger segment B is equal to the ratio of the larger segment B to the smaller segment C. In other words, A by B equals B by C. This is the magic and wonder of the golden ratio. It has unique mathematical properties that distinguish it from other numbers. It is the only number whose reciprocal is 1 less than itself. In mathematical terms, this can be expressed as 1 divided by phi equals phi minus 1. Furthermore, phi is the only number whose square is 1 more than itself. This can be expressed as phi squared equals phi plus 1. The discovery of the golden ratio is not attributed to a specific individual. It appears that people have been rediscovering it throughout history, which explains why it has so many different names. There is evidence to suggest that ancient mathematicians from regions such as Babylon and India were aware of the golden ratio. However, our understanding of it largely stems from the discoveries of ancient Greece. Pythagoras, an ancient Greek mathematician and philosopher, is often credited as one of the pioneers in discovering the golden ratio. It is believed that Pythagoras and his followers used the pentagram, a star with 5 points created by drawing a continuous line in 5 straight segments, as a symbol for their school. This is similar to a pentagon, which is a polygon with 5 sides. Another renowned Greek philosopher, Plato, made significant contributions to philosophy, mathematics, and the natural sciences. In one of his dialogues, Timaeus, written around 360 BCE, Plato presents a cosmological theory where the universe is composed of 4 elements: earth, air, fire, and water. Each of these elements is represented by a Platonic solid, also known as a geometric solid. Plato associated each of these 4 geometric solids with the elements. The tetrahedron represents fire, the cube represents earth, the octahedron represents air, and the icosahedron represents water. Each of these solids is regular, meaning that its faces are all the same shape and size, and each face meets the same number of other faces at each vertex. Additionally, there is the dodecahedron, the 5th Platonic solid, which Plato associated with the universe itself. A dodecahedron is a solid with 12 faces, each of which is a regular pentagon. This is why the pentagon holds significance. In the Timaeus, Plato discusses a mean relationship between 3 numbers, thought to be a precursor to Euclid's extreme and mean ratio, also known as the golden ratio. Plato wrote, "When the mean is to the first term as the last term is to the mean, they will all by necessity come to be the same, and having become the same with one another will be all one." However, it remains unclear whether this is a description of means in general or a specific reference to the golden ratio. Euclid, a mathematician who lived in ancient Alexandria around the 3rd century BCE, is also known as the father of geometry. He authored a book named Elements, now known as Euclid's Elements, which is a collection of 13 books containing illustrated definitions, postulates, propositions, and proofs. These books cover a range of topics, including geometry, number theory, proportions, and incommensurable lines, which are lines that cannot be expressed as a ratio of integers. Euclid's work is foundational to the development of logic and modern science, and is considered one of the most influential textbooks ever written. The first printed edition of Euclid's Elements was produced in 1482, following the invention of the printing press by German blacksmith Johannes Gutenberg. This is one of the first math books ever printed. Only the Bible has more printed versions. Notably, Abraham Lincoln studied Euclid's Elements intensively to hone his logical thinking skills. The influence of Euclid's work extends beyond the realm of mathematics and into the arts. In 1922, American poet and playwright Edna St. Vincent Millay penned a poem entitled "Euclid Alone Has Looked on Beauty Bare," attesting to the enduring impact of Euclid's work. Einstein called Euclid's work a holy little geometry book. In this book, Euclid talked about something called the extreme and mean ratio many times. This is just another name for the golden ratio. Euclid showed how to get this golden ratio using shapes and lines, including a pentagram. In his Elements, he gave a step-by-step guide for making a shape that shows the golden ratio. In Proposition 30 of Book 6, Euclid is talking about dividing a line segment AB in a special way called the extreme and mean ratio. Here's what he asks us to do. First, make a square ABHC. The sides of this square are the same length as our original line segment AB. Then, make a rectangle GCFD. This rectangle should have the same area as our square ABHC. Then, make another square GAED. This square is part of the rectangle. If the length of line segment AC is 1, then the area of the square ABHC is 1. If the length of line segment AC is 1, then the area of the rectangle CFEA is 1 divided by the golden ratio. Furthermore, the area of both the square GAED and the rectangle BHF is 1 divided by the square of the golden ratio. In Book 2 of his works, even before he introduced the concept of ratios, Euclid presented a construction. Here's a simplified explanation. First, find the midpoint E of the line segment AC. This means you need to find the point that is exactly halfway along the line segment AC. Next, draw an arc with a B as the radius. An arc is a part of the circumference of a circle. In this context, Euclid is instructing us to draw an arc using EB as the radius. Finally, measure the lengths of the segments CF and AF. By using the arc, we can find out the lengths of these two line segments. This process allows us to explore the geometric principles that Euclid laid out in his works. In Proposition 11 of Book 2, Euclid demonstrates a method to divide a line segment, which he labels AB. Here's how he does it. He forms a rectangle, which he labels BDKH, using the entire line segment AB and a portion of it, which he refers to as BH. Interestingly, the area of this rectangle is equal to the area of a square, which he labels AFGH. This square is constructed on the remaining segment of the line, which he labels AH. Further examples of the extreme and mean ratio are on the screen. Now let's delve into three-dimensional space. The final proposition describes the golden ratio relationship between a cube and a dodecahedron. In Proposition 17 of Book 13, he constructs a dodecahedron and inscribing it in a sphere. The side of the dodecahedron UV is proven to be an irrational straight line, also known as an apotome. As a corollary, when the side of the cube NO is divided in an extreme and mean ratio, the larger segment RS is the side of the dodecahedron. In the final example, Euclid demonstrates that the side of the dodecahedron segment UV is an apotome. This means it's the larger of two irrational segments that together form a rational line equivalent in length to the side of the inscribed cube segment NO. To illustrate this relationship, the sides of the cube are bisected at points GHKLMN and O. Segments GKHLHM and NO are then connected to represent the width of the cube. Segments NPPO and HQ, which represent half the width of the cube, are divided in an extreme and mean ratio at points RS and T. Since segments RU and SV are at right angles to the cube, the length of segment RS, which is the greater apotome to the rational line NO, equals the length of segment UV. This segment represents a side of the equiangular and equilateral dodecahedron UBWCV. Pythagoras, known for his eponymous theorem, stated that a right triangle with sides of length A, B, and C, where C is the hypotenuse, has the relationship that is a squared plus b squared equals c squared. Similarly, phi is the only number whose square is one more than itself. 2,000 years after Pythagoras, German mathematician and astronomer Johannes Kepler noticed a similarity between these two equations. As he wrote, geometry has two great treasures. One is the theorem of Pythagoras, the other the division of a line into extreme and mean ratio. The first we may compare to a mass of gold, the second we may call a precious jewel. Kepler realized that if you let A be 1, B be square root of phi, and C be phi, then both equations are satisfied. This means that a triangle with sides of lengths 1, square root of phi, and phi is a right triangle. This triangle is now known as the Kepler triangle. This triangle is unique because it links the Pythagorean theorem with the golden ratio. Kepler observed another characteristic of this triangle. He wrote to his former professor Michael Mastlin, if on a line which is divided in extreme and mean ratio one constructs a right-angled triangle such that the right angle is on the perpendicular part at the section point, then the smaller leg will equal the larger segment of the divided line. Here, he is referring to the two legs of the triangles below with a dimension of 1. Simply he means that when you draw a line perpendicular to the hypotenuse of the Kepler triangle, it passes through the right angle and divides the hypotenuse into two segments. The lengths of these segments are in the golden ratio. Furthermore, the two triangles that result from this division are similar to the original Kepler triangle. This means they have the same shape, but not necessarily the same size. The sides of these new triangles are proportional to the sides of the original Kepler triangle, and the angles are the same. This property is an example of self-similarity, which is a characteristic of fractals. It shows how the golden ratio, Pythagoras theorem, and geometry are all interconnected. The 3-4-5 triangle is a special right triangle, distinguished by its sides being in an arithmetic progression. In this progression, each successive term is obtained by adding a common difference. Conversely, the Kepler triangle is unique because its sides are in a geometric progression. In this type of progression, each successive term is obtained by multiplying a common ratio. To put it simply, in an arithmetic progression, the difference between consecutive terms is constant, while in a geometric progression, the ratio between consecutive terms is constant. Firstly, let's discuss the Pythagorean or 3-4-5 triangle. Its sides are in an arithmetic progression. This implies that if you start with the shortest side, which is 3, and add the same number, 1, each time, you get the lengths of the other two sides, 4 and 5. Mathematically, this can be represented as 3 plus 1 equal 4 and 4 plus 1 equal 5. On the other hand, the Kepler triangle sides are in a geometric progression. This means that if you start with the shortest side, 1, and multiply by the same number, square root of phi, each time, you get the lengths of the other two sides. Mathematically, this can be represented as 1 times square root of phi equals square root of phi, and square root of phi times square root of phi equals phi. Now, let's discuss about pentagram. Inside the pentagram, you can find two types of triangles that have sides in the golden ratio. These are the golden gnomon and the golden triangle. The golden gnomon is an obtuse triangle, a triangle with one angle greater than 90 degrees. And the golden triangle is an acute isosceles triangle, a triangle with two equal sides and all angles less than 90 degrees. These golden triangles form the basis of the Penrose tiling, a pattern discovered by mathematician and physicist Roger Penrose. The Penrose tiling is a non-repeating pattern that covers the entire plane without gaps or overlaps, and it's composed of shapes that are related to the golden triangle. Both Pythagoras and Johannes Kepler viewed mathematics as a universal language, evident in everything from the vibrations of a stringed instrument to the motion of the planets. Pythagoras is credited with discovering the relationship between the length of a string on a musical instrument and the pitch of the note it produces. He found that the pitch of a note is inversely proportional to the length of the string, meaning shorter strings produce higher notes, while longer strings yield lower notes. Furthermore, Pythagoras is thought to have associated the orbital frequencies of different planets with inaudible hums, a concept known as musica universalis, or the harmony of the spheres. This theory suggests that each planet emits a musical note based on its orbital frequency, and collectively, the planets create a harmonious symphony that is beyond our auditory perception. Johannes Kepler, on the other hand, had a profound interest in the harmony and geometry of the universe. In his book Mysterium Cosmographicum, published in 1596, as well as his 1619 book Harmonics Mundi, he proposed a model of the solar system. In this model, the orbits of the 6 known planets could be explained by nesting the 5 platonic solids, each within a sphere. The outermost sphere represented the orbit of Saturn, the furthest known planet at the time. Although this model was later proven to be inaccurate, it reflects Kepler's belief in a universe governed by harmonious geometric relationships. Kepler continued his exploration of the cosmos, and in 1617, published the first volume of Epitome Astronomiae Copernicanae. In this work, he unveiled his most significant discoveries: the true elliptical nature of planetary orbits, and the first of his 3 laws of planetary motion. These 3 laws revolutionized our understanding of the solar system, and laid the foundation for the field of celestial mechanics. They describe how planets move around the Sun, and are fundamental to our understanding of the solar system. The golden ratio is a fascinating mathematical concept that permeates various aspects of life, from art and architecture to nature and the cosmos. Its unique properties and relationship with the Fibonacci sequence have captivated thinkers for centuries, leading to profound insights and beautiful creations. Whether we're aware of it or not, the golden ratio surrounds us, offering a glimpse into the inherent beauty and harmony of the universe. As we continue to explore and understand its implications, the golden ratio will undoubtedly continue to inspire and intrigue us, underscoring the profound interconnectedness of mathematics and the world we inhabit. In next video we will talk about Fibonacci sequence. Imagine you're looking at the Fibonacci sequence, where each number is the sum of the two before it, like this: 0, 1, 1, 2, 3, 5, 8, 13, 21, and so on. Now, if you take any two numbers next to each other in this sequence and divide the bigger one by the smaller one, you get a number close to 1.618. The amazing part is, the further along you go in the Fibonacci sequence, the closer this division gets to the golden ratio. So, the ratio of 21 to 13 is closer to the golden ratio than the ratio of 13 to 8. That's the amazing connection between the Fibonacci sequence and the golden ratio. They're two different things, but they're linked in this unique way. The Fibonacci sequence is used in various aspects of life and nature. It's used in financial markets for technical analysis, appears in the structure of honeycombs by bees, and can be seen in the arrangement of flower petals and tree branches. Even the spiral patterns of galaxies follow principles of the Fibonacci sequence. Even our own bodies exhibit signs of the sequence. Our bones grow according to Fibonacci ratios,